In this video, we will be naming and determining the domain of various functions. The domain of a function is a set of all possible inputs, or if we have a function of x, we can say the domain is a set of all possible x values. To determine the domain, there are two rules to consider. Number one, we cannot divide by 0, and number two, when dealing with the set of real numbers, we cannot take the square root of a negative number. Our first function is f of x equals x squared plus 3x minus 10. This is a polynomial function of degree 2, which we call a quadratic function. And now the domain is going to be the set of all possible inputs or x values, and we can take any real number, square it, and add 3 times the real number, and then subtract 10, and therefore the domain is all real numbers, which using interval notation is the open interval from negative infinity to positive infinity. Next we have f of x equals 5x plus 7, which is a polynomial function of degree 1, and therefore we call this a linear function. And again, for the domain, we can multiply 5 by any real number and then add 7, and therefore once again the domain would be all real numbers, which is the open interval from negative infinity to positive infinity. If we take a look at these two graphs, because the domain is a set of all possible inputs or x values, we find the domain along the horizontal or x-axis, and because this graph moves to the left and right without any holes or breaks, this does verify the domain is all real numbers. So this would be the graph of the domain of the given function. And the same thing for the linear function. It moves to the left and right without any holes or breaks, and therefore the domain is all real numbers. Next we have f of x equals the square root of the quantity 36 minus 3x. This is a radical function, or more specifically, a square root function. To determine the domain, the radicand of 36 minus 3x must be non-negative, which means to find the domain, we must set 36 minus 3x greater than or equal to 0. If 36 minus 3x is greater than or equal to 0, it will be non-negative and the square root will be real. And now to solve the inequality, we subtract 36 on both sides to isolate the variable term, which gives us negative 3x greater than or equal to negative 36. Now to solve for x, we divide both sides by negative 3. But remember, when solving an inequality, if we multiply or divide both sides by a negative, we must reverse the inequality. So in simplifying here, we have x on the left. We reverse the inequality, so we have x is less than or equal to. On the right, we have negative 36 divided by negative 3, which is positive 12. This is a domain, so the domain is x less than or equal to 12, but we need this in interval notation. So if we were to graph this, the interval includes 12, so we have a closed point on 12, and then values get less than 12 moving to the left, approaching negative infinity, and therefore using interval notation, the domain is from negative infinity to positive 12. Because it includes positive 12, we use a square bracket to the right. So this is the domain using interval notation. Next we have f of x equals the square root of the quantity 2x minus 8. Again, this is a radical function, or more specifically, a square root function. The radicand must be non-negative, and therefore to find the domain, we must set 2x minus 8 greater than or equal to 0. We add 8 to both sides, giving us 2x greater than or equal to 8. Divide both sides by 2. Simplifying, we have x is greater than or equal to positive 4. Again, if we graph this, we have a closed point on 4, arrow to the right, where values get greater than 4, approaching positive infinity, and therefore using interval notation, we have the interval from 4 to infinity, where the interval is closed or includes 4, so we have a square bracket to the left, a parenthesis to the right. Looking at these two graphs, we can see the domain of this first square root function is less than or equal to 12, or from negative infinity to 12. And the domain of the second square root function is x greater than or equal to 4, or from 4 to infinity. Next we have f of x equals the cube root of the quantity 4x minus 6. Again, this is a radical function, or more specifically a cube root function. Remember, we can take the cube root of both a positive and negative number as well as 0, and therefore the domain of the cube root function is going to be all reals, or the open interval from negative infinity to positive infinity. Next, we have f of x equals 19. Because the output or function value is always 19, this is called a constant function. And again, the input or x can be any real number. It's just the output will always be 19. Because the input can be any real number, again, the domain is the open interval from negative infinity to positive infinity. Looking at these two graphs, we can see the graphs move to the left and right without any holes or breaks, which graphically verifies the domain is all reals for the cube root function as well as the constant function. Next, we have f of x equals x cubed minus 4x. This is a polynomial function of degree 3, which is called a cubic function. For the domain, we can take any real number, cube it, and subtract 4 times the real number, and therefore the domain is all reals. Next, we have f of x equals the quantity x plus 1 divided by the quantity x minus 6. This is a rational function. A rational function is a ratio or quotient of two polynomial functions, or in our case, we have a ratio or quotient of two linear functions. And now to find the domain, because division by 0 is undefined, we need to determine what value of x will make the denominator equal to 0. Once we find that value, we must exclude that value from the domain. So to find the domain of this rational function, we first set x minus 6 equal to 0. Solving for x, we add 6 to both sides, giving us x equals 6. Which means the domain of the rational function is going to be all real numbers except 6. So let's graph this on the number line. We want to graph all real numbers except 6. So let's say this is 0 and this is 6. To exclude 6, we have an open point on 6, and then we graph all the other real numbers to the right and to the left. So to the right we approach infinity, to the left we approach negative infinity, which means using interval notation, the domain is going to be from negative infinity to 6. It does not include 6, so we have a parenthesis to the right of 6, union. We use this u for union, and then from 6 to infinity, again not including 6. This is the domain using interval notation. Let's look at these two graphs. Again, we can see, looking at the cubic function, the graph moves to the left and right without any holes or breaks, which verifies the domain is all real numbers. And now for the rational function, notice how there is a break in the graph at x equals 6, but then from there the graph moves to the right and left, verifying the domain is all reals except 6. And for our last two examples, we have f of x equals x. This is a polynomial function of degree 1, and therefore we can call this a linear function, but because the input and output are both x, more specifically, this is called the identity function. And here, because the input can be any real number, which will be the same as the output, the domain is all reals, which again, using interval notation, is the open interval from negative infinity to positive infinity. And then finally we have f of x equals the absolute value of x minus 3. Because of the absolute value, this is called an absolute value function. And because we can take the absolute value of any real number and then subtract 3, once again the domain is all reals. Let's take a look at these two graphs. Again, notice both graphs move to the left and right without any holes or breaks, which verifies the domain is all real numbers for both functions. I hope you found this helpful.